Alright, we are starting off by discussing how membrane potential of a cell is established. And that starts off with this diagram here. And every cell has a certain concentration of ions inside and outside of it, which overall creates a net negative charge inside the cell versus outside the cell. That comes out to be about negative 70 millivolts for specifically neurons, but somewhere around there in the net negative millivolts. And what causes this resting membrane potential, or this negative 70 millivolt potential, is the concentration of ions here. So within the cell, we're going to have a high concentration of potassium ions, which are positively charged, but we're going to have a low concentration of sodium and chloride ions. And so constantly the cell is going to be pumping within the sodium potassium pump, it's going to be pumping in 2 potassium ions for every 3 sodium ions leaving. And with that, you would think, oh, it's kind of strange that having potassium inside the cell is going to cause a negative charge. But the negative charge isn't caused by the actual potassium entering the cell. It's caused by the potassium leaving the cell. And so when potassium leaves the cell, you have potassium here, and every ion it's not an independent ion, it's charged with a opposite charge. And so when the potassium leaves the cell, it leaves behind that negative charge, which then forms a negative potential. And so as it keeps pumping up, we have these potassium leak channels, which begin to form that negative 70 resting membrane potential. And as far as the Nernst equation plays a role in this, the Nernst equation was developed to figure out what the equilibrium number is for a specific ion with no other ions taking effect. So the example here would be equilibrium would be like equal concentrations on it. It's like equal flow in and out of the cell. And so it would provide the charge you would need, or the equilibrium of that specific ion, to then have the concentrations at equilibrium. So let's say you had a higher number here and a lower number here, and that would cause a positive number, and it would be overall a positive number coming out of there. Now let's see, this should be negative, so it would be a negative number overall. And so with that, it's just going to tell us what amount of voltage is needed to hit that equilibrium at those concentrations inside and outside of the cell. And so that then plays a role into driving force, which talks about how the resting membrane potential, or whatever the potential is of the membrane, compared to this Nernst equation, and how that helps us. So like at normal resting membrane potential, like we said, it's about negative 70, and from calculations from the Nernst equation, we found that the equilibrium of potassium is about negative 95, the equilibrium of sodium is about plus 55. And the way we view this is that, okay, so you subtract the equilibrium from the membrane potential, and it gives you a charge of what the cell, or what the specific ion is trying to reach. And so for potassium has a plus charge inside the cell. So we look at this as potassium would want to leave the cell because of that plus charge. It doesn't want to be near that plus charge. Versus sodium is at a negative charge inside the cell, and since it's a positively charged ion, it would want to enter into the cell. And that would be the driving force. This is what drives these molecules with voltage. It wants to drive into or out of the cell for potassium here or sodium here.